Well, thank you, Eric, for that kind introduction, and thank you to the Freeman Committee for the invitation to speak tonight. Thank you to the Boston Society of Civil Engineers for hosting this event, and thank you all for being here to listen to what I will talk about this evening. So while I get the slides loaded, there's always this critical little step at the beginning of every talk where you make sure that the IT will function as intended. And it does. So we're ready to go. I'm going to talk today about desalination, its value, its pros and cons. I'm going to focus principally on energy consumption issues in desalination. As Eric mentioned, I'm from the mechanical engineering department at MIT. Much of my work is around energy, thermodynamic analysis, and related things. And transport processes, in particular, have a great deal to do with how desalination systems function. So I want to show a few illustrations just to get going. This is a picture I took when I was in Chile, in the Atacama Desert north of Copiapó. This is the world's driest desert. It receives an average of about 3 millimeters of rain annually. Some parts of this desert have never recorded any precipitation. And so the water that people have there, they're receiving primarily from rivers that run down from the Andes, which are about 100 kilometers inland. The city of Copiapó had one such river. It's in a mining area, population of around 150,000 people. But the desert here is not simply an area where people are mining, particularly up in the foothills of the Andes. It's also an area where people are growing grapes for export. It turns out that if you irrigate under these conditions, you get great big grapes that can be sent to Asia and sell at sort of $1 a piece price point. So between that and the demand for copper in China, the demand for water from these rivers has risen quite steeply. The river in Copiapó has been dry for 15 years. And as a result, they've had to look for other solutions for water supply. I was in Brazil last March. And at this point, they were in the midst of a 4-year drought. This is one of the main reservoirs in Brazil. You'll see that it's rather empty. Now, drought was part of the problem here. This is in Sao Paulo, a city of 20 to 30 million people and really a 60 million person sprawl that goes into Rio. The drought's part of the problem. Another part of the problem is that a lot of the sewage is discharged into the surface water without treatment. So the rivers that do run through the city are not very usable. There's not good stormwater management. And if you've been reading the papers, you'll notice the government there is a bit ineffectual. With the result that they've had a very hard time getting solutions in place. Business leaders, NGOs in Sao Paulo are trying to solve these problems on their own because they don't rely on the government at all anymore. This is a by now famous picture. This was the world's 4th largest freshwater lake, the Aral Sea. It is the size of Lake Erie plus Lake Ontario, to give you a sense of scale. Like those lakes, it had cities around it. It had a fishing economy. The 2 rivers that fed this lake were diverted for agriculture in Uzbekistan, and over a period of a couple of decades, the lake dried up. And as it dried up, it took the cities down with it. It eliminated the fishing economy, and the environment there, in fact, has become quite hot and dusty without the moderating influence of the lake. These are some charts showing groundwater decline, 1950 to 2007. This is in meters, and you can see some areas here in the Ogala Aquifer in central United States where the water table has fallen by more than 50 meters. And this other chart is the Central Valley in California, and again you'll see that in some places the water table has fallen by more than 120 meters as a result of water pumping principally for irrigation. And so a completely different setting, a completely different problem. This chart shows it in red areas where the human withdrawal of water is essentially equal to the net precipitation over land. The significance of that number is that net precipitation over land is our renewable supply of water. That's what we get renewably. You can pump out an aquifer and drain it, but it doesn't come back unless you're taking it out only at a rate at which it can recharge. So it's very significant when we start to use as much as we're getting renewably because it means water scarcity ensues in a significant way. What's important about this chart, apart from the fact that water scarcity is very widespread, is that it's very contextual. You have rich countries, you have poor countries, you have part of a country, not part of a country. You have regions by the coast, regions inland, regions that are generally fairly arid, perhaps in the Gulf, regions like Florida, which are generally pretty wet. And so in every case, it's a different challenge and a different set of problems. And what's driving all of this, and what's making it worse, and why there is so much concern about water scarcity, is the rapid rise in human population. We are on track to have 5 times as many people in 2050 as we had in 1927. And those additional 8 billion people have to be supplied by the same renewable source of water that we had in 1927. That's not really a dial you can turn up. The rain falls. And so this is really the major driver behind water scarcity, human population growth. Rising standards of living affect this as well. I'll show you some numbers on that later on this evening. And also, of course, the problem of climate change in the background. And what is it going to do to the frequency and severity of droughts, to our ability to store rainwater if it's all falling at a single point in a heavy storm, and so on. But for all of this, the world is covered in water. Arthur C. Clarke remarked that we should call the planet ocean rather than Earth. There's no shortage of water in that sense, and particularly for cities and coastal regions, you have the opportunity to think about how you might use seawater to produce fresh water. If you can find ways to convert, that is to desalinate this water, that are energy efficient and that do not destroy the marine environment. And so these are the engineering problems that, in the end, are of greatest interest to the work I do. How can you do this without making it too expensive, too much carbon, or damage marine life? So I'm going to recap some things that you've certainly seen from time to time, just to get some terminology out. I want to say what I mean by osmosis and what I mean by reverse osmosis. So this picture up here shows in orange a membrane that water can pass through but salt cannot. You can produce a membrane like that by having appropriate charge groups on the surface. Something called Donan exclusion will prevent ions of one charge from entering, and that in turn, for electroneutrality of the solution, prevents ions of the other charge from entering. And so if you have a case where you've got saline water on one side of this membrane and pure water on the other side, only the water can be transported. And there is a tendency for water to move from the pure side to the saline side in a drive toward equilibrium. So the drive toward chemical equilibrium then causes the water flow. The tendency as well can be characterized by what we call osmotic pressure. So there is effectively a pressure for water flow, which I'll call pi, and I'll refer to from time to time this evening. Pi, the osmotic pressure, is essentially proportional to the salinity. For seawater, the osmotic pressure is almost 30 atmospheres relative to fresh water. So you have a fairly significant driving tendency. On the other hand, if you come back to this system and you apply a hydraulic pressure on the seawater side, you can reverse the flow and you can actually drive water through to the pure water side. And so the process of reverse osmosis is a process in which you'll apply pressure here sufficient to overcome the osmotic pressure corresponding to the water salinity, at least 30 bar in the case of seawater, and you'll force fresh water out of the seawater through the membrane. The flux of water, say cubic meters per square meter of membrane area, is the difference between the hydraulic pressure and the osmotic pressure of the two streams, and the constant of proportionality is something called the permeability of the membrane, which I'll talk about a little bit here and there. So this brings me back to Copiapó. Copiapó did not have surface water, but they did have groundwater. They had brackish groundwater at a salinity of about 3,000 parts per million. So Copiapó began pumping up groundwater and desalinating it by reverse osmosis. This is, in fact, one of the 2 plants they have. The groundwater is brought in. There's some pre-treatment initially. It comes to these high-pressure pumps. The pumps run approximately 9 bar, 9 atmospheres, and the pressurized water is then taken into these pressure vessels where it's passed through membranes. And coming out of these 3 trains of RO, you get about 142 liters per second, or maybe 8,000 cubic meters of water per day. The membranes themselves are spiral wound in modules like the one I'm showing here. This has a dimension of 1 meter length and 20 centimeters diameter. And I'll show you the flow path through this in a few minutes. but that's how the membranes are packaged. One module like this contains approximately 40 square meters of active membrane surface. So it is a very compact device in that sense. Now, I said energy when I started, and I want to start then by saying what the limits of energy requirements are for desalination. As a thermodynamicist, I look at that RO plant using a control volume. I look at saline water coming in one side, perhaps seawater, a stream of fresh water coming out, and then a concentrated brine. This carries all the salts that I took out of the fresh water, and in a typical case, it contains about half of the incoming water volume. The separation of these requires work in a thermodynamic sense, and that work is then provided by the desalination system to perform the separation. What is the work? The work is essentially the pumping work of the pumps that drive the water, or if you like, it's the electrical work that turns the motor. And this work has a distinct limit. You can apply the first and second laws to that control volume. If you assume the system has no losses, the minimum energy required to recover about half the water from seawater is 1 kilowatt hour of electricity per cubic meter per 1,000 liters of water. Cubic meter is about 265 gallons for reference. That's the best you can ever do. Today's systems, state-of-the-art systems, are running between 2 and 4 kilowatt hours per cubic meter, and the reason they differ is because of inefficiency. And again, as a thermodynamics person, I think of the inefficiency as a source of entropy production. The system is not reversible as a result of various losses, losses in the pump, losses through the membranes, losses to hydraulic friction, and so forth. And that difference then is what you would like to reduce in order to drive the working system toward its thermodynamic limit of performance. Now, every now and then, in fact quite frequently, maybe once a year, somebody will invent a new membrane or a new process. They'll get very excited and they'll make a statement like this one. The new membrane is going to reduce the energy requirement by a factor of 100. Well, from what I've just shown you, the current state of the art is within a factor of 2 or 3 of the best you'll ever do. And you know without evaluating this claim that it's incorrect. What's happened in this case is that somebody's looked at a membrane that has 100 times the permeability, and they presume that that somehow means 100 times less energy. But the systems are a little more subtle than that. Now, the number I showed you for the work requirements, minimum work requirements, were for saline water with the composition of seawater and with the total dissolved salts of seawater. If I used a different composition, if instead of having something that's mostly sodium chloride, as seawater is, I had something that was zinc sulfate at the same mass concentration, I would have much less energy required. And at a glance, that may seem obvious, but it's very important as you start to think about the variety of waters that you might want to desalinate. It turns out that seawater around the world has more or less the same proportions of dissolved ions. It can be saltier or less salty depending on rates of evaporation and rates of freshwater inflow from land. But in general, you have about 80% sodium chloride and similar proportions for calcium, sulfate, carbonate, some other common ions. If you're dealing with groundwater, the compositions are different and the proportions are different. So you have to be a little careful in just thinking you have diluted seawater. If you're dealing with water from various industrial processes, perhaps from oil and gas production, you again have very different compositions. And I want to mention this topic in particular because there's been so much attention and so much concern about shale gas production, unconventional oil and gas, and in particular about the water that's used in that process. Both the water that gets pumped in and received back for hydraulic fracturing, but also the water that's steadily produced by these wells as they run over a period of years. The so-called flowback water comes to the surface within a month or 2 of the fracking operation, and you get perhaps a third of what you put down back. But as the well continues to run, water continues to come up with the oil or gas. That water has been underground for a very long time. It's come to chemical equilibrium, more or less, with whatever rock formation it was pulled from. And so it reflects the composition of the rocks that it's been sitting in. And it's also generally at very high salinity. These are some typical samples. So this is the composition of standard seawater at about 35,000 parts salt per million. You can see the dominant ions in seawater are things like sodium, chloride, calcium, and so forth. If I look at produced water, a typical sample from the Permian Basin in Texas, you'll notice that the proportions are different. You'll notice that you have things in the water at relatively high concentrations, such as strontium and barium. You'll notice that the total salinity of this water is about 6 times that of seawater. It's much saltier water. If I look at similar water from fracking in Nova Scotia, it's only twice the salinity of seawater, and it's mostly sodium chloride. Maybe not surprising given where you're located. And if I go to the Marcellus shales in Pennsylvania, I get another salinity. Again, I might see a lot of barium in the water, perhaps a lot of strontium. These variations in composition are quite important if you start thinking about desalinating that water and cleaning it up. What are you going to do about it? For example, if I go to these calculations I showed you before of the least work of separation for such water, the curve on the bottom for about 3.5% sodium chloride, that's very similar to the seawater curve. You can see that as the percentage of water I recover goes up, the amount of work required goes up. Typically for seawater reverse osmosis, you're going to stop at about 50% recovery. But what's more interesting here is that when I go to these other formations and look at produced water, Permian Basin in Texas, for that water, you're looking at a least work that's almost 8 times as much as the work required to desalinate seawater. So the composition right away sets a baseline that says you've got some challenges. You have some other challenges as well, because as you start to remove water from seawater, from produced water, from any of these things, you'll hit a point at which you reach the solubility limits for one ion or another. For the waters from Nova Scotia, you don't have a lot of stuff that's insoluble. In fact, the first thing that really starts to precipitate is sodium chloride, which is often actually relatively easy to clean out of your equipment if you do have fouling. On the other hand, if you look at the water from Texas, almost immediately you're coming out near saturation with barite. You've got strontium sulfate as well. You've got calcium sulfate. These things are coming out right away. And what that tells you is that before you can even think about desalinating that water, you've got to do some type of pretreatment to get rid of the strontium, get rid of the barium, remove the sulfates. It's typically done by chemical softening of some sort. And then you can go on and desalinate whatever remains. I mentioned membrane processes. I want to say some things about thermal processes. Distillation is, after all, the oldest of the desalination technologies. It goes back to antiquity. A modern distillation plant is much more thermally efficient than simply boiling water and condensing the vapor would be. Because when you boil water and condense the vapor, you're giving up all of the energy you use to vaporize that water in the condensation step. Water requires something like 2.2 megajoules per kilogram per liter of water to vaporize. It's a lot of energy when you're doing it at large scale. And so a well-designed thermal desalination process will attempt to capture the latent heat as vapor is condensed and to reuse that energy to vaporize more water. And when a system is designed well, the amount of energy you put in is about 1/10 the amount of energy that it would have taken to boil and condense that water. We call that ratio the gained output ratio. And a design goal is to make the gained output ratio large. Now in this case, you've got seawater coming in. It's cold. It's acting as a coolant in a condenser, condensing some vapor. It's doing this through multiple stages, perhaps 20, 30 of them. And finally, it will leave the condensation path here at a temperature of perhaps 70 degrees C. You will top heat it with steam from an adjacent power plant, and then it will come back at 90 C, and you'll start to depressurize it. You'll drop the pressure in each stage 5 to 10 kPa, and every time you do that, you vaporize a few percent of the seawater. And so this vapor is formed by going through each of these stages. The depressurization, by the way, is accomplished by pulling a vacuum at this end and then having a series of weirs. And so it's just a hydraulic resistance stage to stage that allows you to get the pressure drop. The vapor that's formed here condenses and comes out as product water. The whole thing from a thermal engineering perspective is a regenerator, a recuperator. You're recovering the heat you put in to the greatest extent possible, and then you're getting the purified water on the outlet. These systems would operate all the more efficiently if they had a really high temperature on the top side. But you're limited on the high end by scale formation. Above 100 or 110 C, you very rapidly begin to precipitate calcium sulfate, forms hard scale in your equipment. It's not economical to control or remove, so people just don't run beyond that. If you could find a way to do it that was economic, you could make these systems much more efficient. You could probably make a lot of money. This is a representative thermal plant. So this is the multi-stage flash operation that I showed you. Here's one train, another. Behind it is a power plant. And so water is taken into the power plant. It's used as coolant in the condensers. Some of it is also used in the flashing process. Depending on how this system is designed, the water that leaves the plant, the brine leaving, might be blended with some of the coolant from the condensers to dilute it before it hits the ocean. Systems like this also have a limited performance. And to think about that, I simply think about heat at a high temperature going to a low temperature. Remember something called the Carnot cycle from thermodynamics? The amount of work you can produce from a Carnot cycle is related to the amount of heat transferred and the temperature differences. A straightforward calculation will tell you the least amount of heat required to desalinate. Now here I want to be very careful. Heat and work are not the same so far as a thermodynamicist is concerned. For example, to make work, to make electrical power, you use a lot of heat. But you can only convert about half of that heat into electrical power. The rest has to be dumped under the principles of the second law. And so you don't want to add heat to work. In fact, I'm going to give you the performance here in units different than I used before. These are kilojoules. The thermodynamic limit of performance is about 15 kilojoules per kilogram of water produced. Now, a real system, such as the one I showed you in the picture before, requires about 20 times that much thermal energy. It's a long way from the reversible case, very long way. There are a number of reasons for this. One is that the top temperature tends to be very low. Another is that to get reversible performance, or anything like it, I would need very large heat transfer surfaces. That means very large condensers with very large amounts of expensive copper-nickel alloy piping. It would not be economical to build this system strictly for energetic performance. Like all desalination systems, these things are designed to optimize the cost of water as opposed to the energy consumption. And the capex for a system like this can get to be quite high. Now, what I can do to make a comparison to the mechanical system is I could say, well, I got this heat at a certain temperature. I could have left it in the power plant. Right? I could have generated more electricity with another turbine, a condensing turbine. How much electricity could I have made? Well, I could have made something like, say, 14 kilowatt hours of electricity. That's still a lot more than the state of the art for the reverse osmosis systems. On top of that, the system that I showed you back here is circulating enormous amounts of water. The electrical work to pump that water is typically 3 to 4 kilowatt hours of electricity all by itself, just for the pumps, which is to say it's already just as much as the reverse osmosis process. Now, that's not to say there isn't interest in using heat to desalinate, because we have sources of low-grade heat, degraded heat from one source or another, perhaps simply a solar thermal panel, which can give you hot water at a temperature of 50 or 100 C, depending on how you design it, maybe more if you cut the flow rates down. And so you can start to look at the impact of the high temperature on the minimum amount of work required. For example, I showed you numbers that corresponded to a high temperature of about 100 C. But if the high temperature is only 50 C, the minimum amount of work is much greater. Which is to say that these degraded sources of heat are not very efficient ways to desalinate. And for that reason, most interest in solar-driven desalination is based on photovoltaics, which directly produce electrical work from solar energy, and which have become cheaper and cheaper as production volumes have come up. So almost any time you see somebody trying to do solar-driven desalination, off-grid desalination, the driving energy source is going to be a solar panel, and that's really very much the directions things have gone. Groundwater, of course, is the other place we might look at desalination. There's a lot of water around that is brackish. for one reason or another. This is a chart from the U.S. Geological Survey, some work that was published by McMahon and others just last fall. USGS has been surveying brackish groundwater across the United States. They haven't released the data sets fully yet, but they did publish this graph. These red sites here are wells with TDS of 5 to 10,000 parts per million, which is to say between a sixth and a third the salinity of seawater. It's pretty brackish stuff. These red circles are overlaid on top of other less brackish wells, but you can see from the chart that there's an awful lot of brackish groundwater available. And so people are interested in the question of whether they can pump some of that up and desalinate it and use it for irrigation or even for drinking or for some other purpose. You, of course, also have to ask yourself whether it's recharging or not at adequate rates. There are a bunch of hydrological questions that go with the use of that resource. But nonetheless, this becomes very interesting in particular contexts. For example, in India. This is some work done by my colleague Amos Winter. He's a professor at MIT, and his student Natasha Wright. And they've been interested in looking at how to provide more water, mostly to farmers in rural India. And in particular, up here in Gujarat and Rajasthan, the groundwater is really quite brackish. The government has had a program of subsidizing the pumping of water with grid electricity, which has compounded a number of other issues. It's said to have contributed to the major blackout they had in India a couple of years ago. And Amos and Natasha observed that these regions that have very brackish groundwater also tend to have fairly high solar availability. So a lot of solar incidence. If you've been to Gujarat, it is very dry and very sunny, for example. And so their idea is to use solar panels, electrical panels, and a process called electrodialysis to separate ions from brackish groundwater. Electrodialysis has been around a long time. It's a pretty well understood and robust process. It's based on membranes that will pass ions of one charge or another. And so if you have an electric field here, negative ions will go toward the anode, cations will go toward the cathode. These anion exchange membranes will pass anions but not cations. And so you can see that the stream in the middle is going to concentrate as it goes through the field, whereas the streams to either side of it will dilute. So this is an electrochemical separation. And it happens that there is a sweet spot for this technology relative to reverse osmosis. The energy required to desalinate by electrodialysis is less than reverse osmosis by a significant amount within a window of 1,000 to about 3,000 ppm, again depending on some design variables. So they're interested in coupling solar panels with ED to go into India and address some of these challenges. So I've given you a range of technologies at this point. This is a map or a pie chart from 2013. It's data from the Desal database. What you see is that worldwide, most of the installed capacity, about 65%, is reverse osmosis. You have fairly large installations of the flash process I showed you, a related process called multi-effect distillation, just a very little of electrodialysis, and then some other technologies. Total of, actually today, close to 90 million cubic meters per day of water are produced by this means. As it happens, that's equivalent to about 6% of the world's domestic water consumption. It's not all used that way. Some of it's used for power plants. For example, in Gujarat, the world's largest oil refinery has a distillation plant that provides all of its water. But if you look at the total water withdrawal in the world, it's on the order of 1% and continuing to grow. Now, about 50% of seawater desalination is done with these thermal technologies, which I've already told you are not very efficient. You might ask, why are people using these? Well, they're great big plants with very long lifetimes and large capital investment. You can retube one of these things and keep running. And so these plants went online many years ago, and they will stay online for some time to come. But there are relatively few of the thermal plants being built now. And even in the countries that have a lot of thermal plants, typically the Arabian Gulf states, they're building more and more reverse osmosis plants. And that's really the direction things are headed. Largest capacities that are installed, Saudi Arabia, Kuwait, United Arab Emirates have very large capacities. As it happens, the United States has a great deal of desalination. but we're also a very big country and you just don't notice it. It's not a huge fraction of our production. The Spanish have gone heavily that way, the Chinese are moving that way, and of course the Israelis are getting most of their water at this point that way. You might be wondering, what does this all cost? You know, cost is always a big concern around desalination, so I'm giving you some breakdowns here. The pie chart is the cost of water, all right, dollars per cubic meter roughly. About a third of the cost of water from reverse osmosis is energy, it's the electricity. About 40% comes from CapEx, and the balance is OpEx divided amongst the categories you can see over here. If you ask what's the EPC cost, the engineering and construction cost, these are the major drivers. High alloy steel and pumps are almost a quarter of the cost of a typical plant. Other materials, engineering services, legal and other services. Finally, pretreatment, intake and outfall for the plant. And surprisingly, down here near the bottom are the membranes and pressure vessels. And for all the attention given to membranes, they're actually not the most costly part of the plant by a good stretch. What this also tells you is that as you think about engineering these plants to cut the cost, you're probably interested in seeing what you can do to reduce the amount of high alloy steel or the number of high pressure pumps you have, as opposed to improving the membranes. So what governs the efficiency? This is a representative flow path of a reverse osmosis plant. The membranes are in this box over here, so high pressure seawater enters here, goes through the membranes and comes out as low pressure purified water. High pressure brine leaves over here. It doesn't lose a lot of pressure, maybe a couple of bar against perhaps 70 bar as it goes through the membrane. So there's a lot of energy in the brine leaving. It might be 40% of the flow. And that energy is recovered through something, you can think of it as a turbocharger pump. The actual devices, the pressure exchangers, are rotary machines. They're really very clever engineering. And they're very efficient at transferring this pressure to some of the feed. The rest of the feed is taken through a high pressure pump and brought in here. So you can ask, what is the biggest source of loss in here? The pumps are actually pretty efficient. In fact, for the largest plant, this high pressure pump has an efficiency in the range of 89%. These are really efficient pumps for reasons that are clear. Most of the losses are occurring as the water goes through the membranes. You get a very large pressure drop here, and you can't do a lot to recover it under the current designs. And so this loss, the so-called irreversibility, is what I call entropy production. How's that happening? This is a schematic of one of the membrane modules. We've got pressurized water coming in here, seawater, and it's passing through the membranes. The water that comes through the membranes comes through them as pure water in blue. The blue is carried through a center tube and taken out the end. There's basically a thrust support down here. And you've got then increasingly saline water that leaves. If you take half the water as purified water, the other half comes out as a concentrate with about twice the salinity. Now, what's going on? As the water travels through here, it's entering with an osmotic pressure that might be 25, 28 bar, depending on the salinity. By the time you get out, you've doubled the osmotic pressure of the brine. In order for water to flow through the membranes down at this end, the hydraulic pressure down here needs to be greater than the osmotic pressure there. And so you've got to set some higher pressure down here, and the only way to do that is to set a really high pressure at the inlet. So much of this device is greatly overpressured relative to what it ought to be if you just wanted the water to flow gently through. And it's a calculation, but you can find that the difference between these two squared is essentially the size of the entropy generation. So your engineers, what do you do about this? Well, one thing that you might consider doing is coming in and saying, well, how about if I just pressurize to 40 bar and let the pressure drop, and then I have another pump and I pressurize again and pressurize again, right? You will cut down on the overpressurization, and that will clearly lower the entropy generation. But it will raise your CapEx. And these are large, expensive pumps, and the result is that it's hard to do that economically. You really need to look at processes that work a little differently. Here's an example of a process that works a little differently. Suppose that I run in batch. I charge up this cylinder and then gradually pressurize it as water flows out through the membrane here. And I keep the pressurization just above the osmotic pressure as the process runs. So I'm never overpressurized. With the result that I can actually cut the energy consumption quite dramatically, perhaps by as much as 60% relative to the process I just showed you. There are some commercial variants. There's one on the market that resembles this process. In fact, it's a local startup. It's called Desalination, based on some technology that came from Israel. And this variation, however, is even more efficient, as you can see from comparing these two charts. This is one that was just patented by our group at MIT. Now, in the thermal systems, you have similar things that you're trying to do. You're trying to limit temperature differences that cause entropy generation. It turns out that the rate at which you produce entropy depends more or less on the difference between the two temperatures through which heat is transferred. So if I have a heat exchanger, say hot fluid this way, cold fluid this way, similar to what I showed you in the thermal desalination plant, when one stream has a much higher product of mass flow rate and specific heat capacity than the other stream, you get a variation in the difference between the stream's temperatures. In this case, the hot stream has a lower heat capacity rate, and so its temperature changes a lot, while the cold stream doesn't change much. That means that I'm generating a lot more entropy on this side of the device than on this side. On the other hand, if you balance the capacity rates, the entropy generation can be minimized. It's not a difficult calculation, in fact, to show that minimum entropy generation in a heat exchanger occurs when the ratio of capacity rates is 1. If you think about something like a membrane process in counterflow, there you're not thinking about heat, you're thinking about differences in concentration or chemical potential. The entropy generation process is very similar. Same ideas about balancing can apply. Or if you think about a humidifier, maybe you want to do a humidification-desalination process. You have the same kinds of ideas. In this case, I've got something, you can think of this as a cooling tower or packed bed. You've got warm water entering the top, cold, dry air entering the bottom. You've got a splash packing inside. Water vaporizes into the air. The airstream now leaves warmer and more humid. In this case, you're putting latent heat into the air, not just sensible heat. And so it's insufficient to think about a heat capacity rate. And instead, what you should think about is just a change in the enthalpy flow rates. You get a modified heat capacity rate ratio. But if you control that parameter very much the same way, entropy generation is minimized when this heat capacity rate ratio, modified heat capacity ratio, is unity. How do I use these ideas? Well, here's an example of a technology that we've worked on at MIT quite a bit. It's called humidification-dehumidification desalination. In this system, you bring saline water in, perhaps seawater, groundwater, or water from hydraulic fracturing, use it as a coolant in a condenser, similar to what I showed you before, top heat it, spray it over a splash packing. And then you've got air flowing through here. Air flowing through here on opposition. The air comes through, it's humidified, you take it over here and condense purified water. You can recirculate this brine as many times as you need to get a decent recovery ratio. So this is pretty neat for the following reason. There's no membrane. Membranes are sensitive. They require pretreatment. They require the pH to be managed. They don't like scale. Everything in here can be cleaned with a wire brush. You've got standard unit ops. These are things that you know how to do. You don't need a new material. It's all basically off the shelf. You do have a problem. In this dehumidifier, you have air and water vapor. Now, when you think about a condensation process, you're bringing water vapor to a condenser surface. It condenses as a liquid and rolls down the condenser surface. If air is in the condenser, it gets swept to the condenser surface, but it doesn't condense. And so air collects near the condenser. That's why you don't want air on a vapor condenser. And so this incondensable gas problem cuts the heat and mass transfer rates by about 2 orders of magnitude. And it is really very much a challenge. That's why if you look at your household dehumidifier, it's got these great big aluminum plates in it. You put in a lot more surface area to overcome the resistance to heat and mass transfer. The effective resistance is 1 over the area, so big area is the solution. However, another way to do this is to use a direct contact process. This is something, again, that we worked on at MIT. You bring warm, moist air into a pool of cold water. You form a bunch of bubbles. The water vapor condenses on the bubble surface. The air flows on out, having been cooled and dried. And the interesting thing is these bubbles are constantly reforming. There's no way for incondensable gas to collect at the bubble surface. So you've eliminated the incondensable gas problem. You've got a very high rate of transport. These systems are violently stirred. And you've got a device which is effectively much more compact and cheaper than what you started with. So this is a pretty interesting concept, to have a bubble column dehumidifier here, a splash packing here. You still have the design problem that the mass flow rates in these two devices are coupled. Whatever goes into one goes out the other. The temperatures in the two devices are coupled. You can't just design the humidifier and then just stick it onto a dehumidifier you design separately. You actually have to design them in tandem, so this is all done with software. You've also got a very strong nonlinearity in this system because vapor pressure rises exponentially with temperature. And so as the temperature of the system goes up, the vapor pressure goes up dramatically. A device like this is critically sensitive to the top and bottom temperature that you're working with. Nevertheless, it has a similar kind of heat capacity rate ratio to what I showed you for a humidifier and, for that matter, for a counterflow heat exchanger. And if you design this so that the heat capacity rate ratio is 1, you actually can maximize the energetic performance of the device. It's a very simple device. There are ways to do this that are more efficient. But the gained output ratio, the energy you put in relative to what energy you would have had to put in to just vaporize and condense is vastly improved by this kind of a design. I want to say a little bit more about these bubble columns. So this is what a single stage device would look like. You've got, say, seawater coming in through a coil here. You've got moist air coming in through the bubbles. They both come toward the temperature of whatever liquid's in the column, right? That's the set point in this device. Now, you can see that I've lost an awful lot of driving potential in this process. I didn't have the opportunity to do something more efficient with just one stage. As a result, my seawater didn't get very warm, right? On the other hand, if I use a series of these trays and go through a series of different temperatures, I can bring the seawater up bit by bit through each of several stages, with the result that instead of having a device that's 30% efficient, I have a device that's 92% efficient. I can do that in about 3 stages of device. What's it look like? Well, here's a little video. It's not a working device, but you get the idea. Moist air coming into pool 1, going into pool 2, pool 3, pool 4, and then the water's coming through the coils from pool to pool in the opposite direction. So very robust, simple technology. My former students took this out and commercialized it. They're currently working in West Texas to remediate water from unconventional oil and gas. And they're doing well, except for one little detail. The price of oil has fallen dramatically since they went into business. So where does this leave us in terms of the overall efficiency of various types of desalination process? When I think about efficiency, I think about what we call second law efficiency. I think about the minimum amount of work, or the least, if you like, exergy that I would have to put into the system to get something done. For example, the minimum work of desalination, the minimum work to pressurize. It's like an isentropic efficiency for a pump, for example. And I think about that relative to the amount of energy that I did put in, the amount of exergy I actually had to add. So, for example, this would be the least work of separation divided by the actual work that went into the RO pumps. Or it would be the least work of separation divided by this Carnot factor on the heat I put into the thermal desalination plant, plus the work I had to put into those pumps that were circulating all that water. This is a proper measure then of how well I'm using the energy and what I'm doing relative to the best process I could have. And here's where a bunch of common systems stack up in terms of the least work of separation and the exergetic efficiency. These are the thermal plants I showed you, typical MSF plants. These are real data from systems that have been described in literature. And you can see that their overall thermal efficiency is in the range of 5 to 10%. Not great. Not really that great. If you look at the seawater reverse osmosis plants I mentioned, working plants, numbers tend to be more like 25–30% overall efficiency. It's a vast difference in the efficiency with which energy is being applied between these. Now again, in both cases, those plants are not designed to impress you with energy efficiency. They're designed to minimize the cost of water to you. I could make the seawater RO plant more efficient by having larger membrane areas, more pumps, lower flux, etc. I could make the thermal plant more efficient by having bigger heat exchangers and more copper. But this is representative of where the state-of-the-art sits now. There's some other technologies here. The so-called forward osmosis process you may have heard of lands in between. Again, there are a number of designs, and depending how it's designed, it's somewhere in this space. Over here we have brackish water reverse osmosis, typical plants. You'll notice the efficiency for the brackish plants is lower than the seawater plants. You probably wonder why. Well, there are two things. The brackish plants tend to be smaller in most cases. Typically, when they design these plants, they're again looking at cost of water, and they find they can get a more economical design by having fewer membranes, not having the pressure recovery device I mentioned, and simply paying a little more for energy. And so there's a trade-off here between CapEx and OpEx that they're making as they design those plants, and that's why they land there. There's no a priori reason that these plants couldn't be up here. And then these are the electrodialysis plants that we have data for, and they're running at a somewhat lower point. The other thing you might wonder about as you think about this efficiency, I gave you efficiency numbers for energy going right into the plant, the electricity going into the reverse osmosis plant, or the heat going into the thermal desalination plant. But these things are also done as co-production, where you're taking primary energy, the coal you burn, well, let's hope you're not burning coal, the clean fuel that you're burning in the power plant, natural gas, shall we say, and you're burning that, and then you're using it to produce electricity and perhaps some steam blowdown. And you could take the steam blowdown and you could drive the thermal desalination plant, or just not have the thermal desalination plant, use some of your electricity to make water. You have choices to make here. And so we can think about this as follows. I have to put some additional amount of energy into this plant in order to drive the desalination plant. If all I wanted to do was to make this much power, then I'd only need, say, Q power plant worth of power to go into my power plant. But if I want to take out some steam here, if I want to take out some power here, I'm going to have to put a little more. And so this is the added primary energy that you're putting into the process. The question is whether somehow a thermal plant might have an advantage here, because you're just taking so-called waste heat, I don't like that term, blowdown if you like, from the power plant to drive the thermal process. You're going to have to blow down some steam no matter what. So we could compute a second law efficiency here, as we did before, looking again at the least work to separate fresh water from salt water, and then looking at the exergy input to this plant. And if I write out the numbers and do some calculations I won't bore you with, you've got the work that you put into the desalination plant divided by the efficiency of the power plant now, or the heat that you put in relative to some temperatures that are appropriate to the process. When I do these computations, here's what I find. Relative to primary energy, seawater reverse osmosis with a combined cycle power plant at 67% efficiency, that's a really good plant, has 10 to 20% overall second law efficiency for separation. But on the other hand, if I look at the MSF plant I showed you and I include the pump work, it's less than 3%. So it's really not a good way. If you're going to burn that fossil fuel, you'd like to burn as little of it as possible for the purpose that you have. You're much better off than going with the membrane process and the thermal process. So let's talk about alternatives. All right, desalination is, what I've been interested in. I'm interested in seeing what you can do to lower the energy of desalination to make it a more efficient process. But there are other ways to get water. And when you're looking for water for a purpose for a municipality, desalination is one option among many, and it needs to be justified before you jump in and use it. So here's some cases to consider. This is a chart that was produced by Cesar Lopez, who at the time was running the San Diego Water Authority. San Diego is a very dry region in Southern California, and San Diego only has about 18% of its water from local supply, whether it's rainwater or available groundwater. They're getting 54% of their water from the Colorado River, About 28% of it comes from the State Water Project up in Northern California and is brought down here. San Diego, and for that matter Los Angeles just to the north, have the problem that they are very large cities in effectively desert regions. In fact, if you know Los Angeles and you know Wilshire Boulevard, runs right through the middle of the city, just south of my alma mater, UCLA. Half the population of California lives south of Wilshire Boulevard, whereas about 80% of the water in California is up here. So it's clear that they didn't design the state right. Right? Could have been designed differently. But they were able to do LA, if you like. LA was able to grow because it was able to find water from remote sources. The first of which, of course, was the Owens Valley. A famous story, if you read Cadillac Desert, if you saw the movie Chinatown. They went up, they posed as ranchers, they bought up the water rights, they diverted the water. Owens Lake is dried up. Right? Nobody's paid for the environmental cost of making Owens Lake go away. Mono Lake was having similar problems. Water was being diverted up there as well. Eventually, you can see this island here. Eventually the water got low enough that there was a land bridge out to the island. And people who have been fighting to keep water in the lake had not succeeded under water rights rules. But as it happened, the island had some endangered species of birds that nested on it. And when the land bridge formed, coyotes were able to get out there and eat the birds' eggs and maybe the birds. So they were able to get the water put back in the lake using the Endangered Species Act. And that was the solution to stop that water transfer. Colorado River, of course, everybody's got their hand into this river. And here's some numbers for you. The Glen Canyon Dam is here. The 100-year average flow at the Glen Canyon Dam is about 500 cubic meters of water per second. When you get down to there are two borders with Mexico, the northern and the southern, because there's a jig-jag here. At the northern international border, the average flow is about 10% of that amount of water. The rest has been taken out, mainly for cities, some for irrigation. And at the southern border, in many years, no water at all flows. In fact, in many years, there's no water flowing into the Gulf of California at all. Right? And that is, if you like, that is an externality that's not accounted for when people look at the price of water and the impact of these transfers. But I'm talking about energy, so let me come back to energy. These are the pumping, simply the conveyance energy for moving water in those aqueducts. Doesn't include any treatment, doesn't include high service pumping in the cities. And so the energy required to pump water from Colorado River into San Diego and LA is about 1.6 kilowatt hours of electricity per cubic meter. The energy required to move it from Sacramento all the way down here to, actually this terminus is in Los Angeles and San Diego's down here, it's 2.6 kilowatt hours per cubic meter. Right, which is comparable to the energy required to do state-of-the-art reverse osmosis of seawater. And so immediately you can make the argument that reverse osmosis applied in Southern California would be carbon neutral or nearly carbon neutral relative to what's being done now. It would also be done without the environmental impacts on the Sacramento River and the Colorado River, etc. So there's more to the question than just energy. But my point here is really that what was the state of the art and the best solution 100 years ago may not be the best solution today. And a reconsideration of alternates may make some sense. Of course, the desalination plant is also drought tolerant, whereas the aqueducts, as we have seen, are not drought tolerant. San Diego, in fact, has recently opened what is the Western Hemisphere's largest seawater desalination plant. It produces about 190,000 cubic meters per day of water. It's equivalent to, say, 7 to 10% of San Diego County's water demand is currently provided by this plant. The energy requirements for the RO stage itself are about 2.7 kilowatt hours per cubic meter. There's additional energy for intake pumping, for pretreatment, and then for pumping it another 10 miles to connect to the city's water main. There's a very long pipeline behind this plant. So all in, the energy is about 3.6 kilowatt hours per cubic meter for this plant. Cost of water, they have a contract to sell this water to San Diego for $1.65 a cubic meter. So that's the contract price. What did this thing cost? Well, it cost about $540 million to build the desalination plant. It's a little higher than some of the EPC numbers I showed you before. but it's in the ballpark within the scope of projects around the world. Financing costs, that is getting the loans and paying the debt service, are a huge part of the cost of this plant. And this underlines the point that how you finance a big project like this makes a big difference to what people are going to pay for it. The conveyance pipeline, now think about this. You're on the coast of Southern California. You're in Carlsbad. This is a nice residential area. A lot of expensive houses. This pipeline snakes its way inland 10 kilometers, 10 miles, through a rather sinuous path, through some very expensive real estate. And it cost them $160 million to get the thing in. That's one of the challenges that anyone will face trying to do desalination in California. Coastal real estate there is very expensive. It's also very well protected. A lot of regulations around it, a lot of people who are interested in seeing that the marine ecosystems are preserved, that the surfers can surf, that there isn't a lot of ugliness along the beach. And so they're working under a number of constraints in this case. Plant was about $1 billion. Now I mentioned marine ecosystems, and I want to come back to this point. At Carlsbad, their plant is located right behind a power plant that's been on that site for about 50 years. The power plant takes in a lot of water for its condensers. Some fraction of that water is then taken into the desalination plant. It's a little bit warmer. It gains about 2 C going through the condensers, so it hits the plant at about 16 C. It then comes out of the plant having its salinity much higher and its temperature approximately the same, where it is then blended with about 100x the volume of condenser water and discharged to the same outlet the plant has been using for condenser water for some time. It relies on tidal mixing beyond that to diffuse and dilute. This is a photograph from the plant in Perth, Australia. The Australians went very heavily into desalination about 10 years ago. They built 6 major plants. Probably the most successful of them were the 2 plants they put up in Perth, which is a very dry area and has continued to use them steadily. The plants in Perth were built in an area that had a sensitive marine ecosystem and a lot of environmental regulation to protect it. And so in this case what they did was to build an outfall pipeline, went a couple kilometers offshore, and they have a 6-acre site where they've got about 20 nozzles like this one distributed at spacings of 20 meters or so. Water is injected with some velocity, as you can see here. They rely on turbulent mixing to diffuse it and to ensure that the salinity decreases to within a couple parts per thousand of background within about 100 meters. The photograph here is one I got from the designer of the plant, a guy named Gary Crisp. It shows the rhodamine dye tests they did. So they simulated all this numerically to figure out how to put the diffusers in. Then they were required to go back and verify it. So they put rhodamine into the water, it's a fluorescent tracer, and they made measurements to confirm that they were indeed getting the dilution that they were required to get under the permits. So this is an example of that case. Gary likes to point out that you've got marine life on the diffuser, but I think that may be oversimplifying a little bit. What's in this water that comes out? Well, salts. The salts that you had in seawater. Depending on the plant, there could be some residual chlorine, which would have a half-life of about 15 minutes in the ocean. Depending on the plant, if they're corrosion byproducts, they could include things like chromium. And so there are some issues to be considered when you think about what you're putting back in the ocean. What are the right concentrations and what's safe? At this point, what I have heard has been a lot of tug-of-war between people on both sides. I think it's an area where more research would go a long way to helping find good designs and good solutions for these plants. And that's ongoing. The other question is intake. When you pull water into one of these plants, you don't want to entrain marine life. And so, you know, to first order, you put screens over the intake to keep big things out. But you've also got to keep the velocities down, because if the intake velocities are too high, small fish get swept onto the screen. They can't get themselves off, and they die. So you have to think about that as a design variable as well. So there's a balance here of how do you design this, how do you control costs, and how do you manage these impacts. The other thing to consider in thinking about alternatives, of course, is consumption. You know, we've seen in the California drought that they had considerable elasticity, and when regulations went in some parts of California, suddenly consumption dropped by 1/3. People were really able to clamp down on what they were doing and to change the rates of use. This is a graph one of my students made showing water consumption per capita. This is based on UN data. I have a comment on that in a minute. But liters per person per day for various countries versus the Human Development Index, which is a measure of lifespan, literacy, GDP and some other things lumped together. You can see that in a number of countries where the Human Development Index is low, the per capita consumption of water is also low. You can also see that in countries where the Human Development Index is high, the water consumption may or may not be high. And it's a little bit difficult to draw a conclusion that there's some correlation between these here, particularly as you get to the higher end where the curve just seems to jump up. And so the reasons why some of these countries are so high on the chart relative to others is not obvious. Germany is a pretty advanced country. Even as my friend Andrew will tell you, the UK is an advanced country. Sorry, Andrew. And the US, of course, is up here as well. So there's something going on here that does not have to do with necessary consumption for standards of living. When I show people this, they immediately ask about pricing. And so what I've got here is some data from Global Water Intelligence. This is a survey from 2014 of water tariffs. This includes separately the water tariff and the wastewater tariff. So this is a combined water sewer tariff. These are in order of what the tariff is in US dollars in that year. And then over on the other side, you'll see daily domestic use. And let me just make a couple of comparisons. This is Australia and Germany. Price of water is about the same. The per capita consumption differs by more than a factor of 2. It doesn't seem that the price, at least at this resolution, at this granularity, explains the difference in consumption. You'll also notice that this number is lower than the one I had on the previous chart. Different data sets, the UN Human Development Report had some numbers in it for US consumption as well, which are much higher than what the USGS would tell you the numbers are. So you have to look a bit at the data and what's being reported and measured. But if I highlight the US on this chart, consumption's about the same as Australia, whereas the price is about $3 less for water. So somehow pricing by itself isn't accounting for these differences. I don't have a full breakdown on this, but I think it's worth pointing out some lack of correlation between consumption and cost. Let me return to energy. These are energy consumption in kilowatt hours per cubic meter for some typical things we do with water. For example, groundwater, pumping it up 120 meters is about 0.6 kilowatt hours. Pumping it 100 kilometers with no grade typically might be about 0.4. The two aqueducts I mentioned are here. Primary treatment, groundwater or surface water, not much energy. Desalination, more energy depending on whether it's brackish or seawater. The thermal process is here. Primary treatment, secondary treatment. Well, look at this, recycling to potable use. Well, that's interesting. So if I make a comparison here, the energy required to recycle water to potable condition is significantly less than it is to desalinate, or for that matter, to go through these dramatic transfers of water over great distance. Of course, the most energy intensive thing we do with water is we heat it. If you want to save energy, save your hot water. But the recycling idea is, I think, a very important one as well, because that's water you've got on hand. Reclamation is common, but recycling to potable use may be a little less common. However, it's done in Singapore at large scale. And the energy numbers that I got from their public utility, PUB, are 0.6 to 0.7 kilowatt hours per cubic meter, far less than seawater reverse osmosis. Singapore uses seawater RO as well because it can't get enough recycled water to meet its demand. But at present, they're meeting about 30% of their supply through these means. The process involves going through standard wastewater treatment, then going through an RO stage, and then finally using ultraviolet to break up whatever organics may have gotten past the membranes. And then it's basically ready to go. They don't call it wastewater. It's used water. Think about perceptions. We just used it. Now we're done using it. We've treated it. We have new water. And so they've worked hard at public acceptance of the technology. And in fact, in the US, there are a number of projects along this line. A number of them came up in Texas during the drought. And San Diego has actually commissioned a much larger water recycling plant than that desal plant that I showed you. Orange County has been doing this for a number of years. they don't actually take the water to direct reuse. They use what's called indirect potable use. They inject it into an aquifer, and they pump it back up later. And that way you have the perception that you aren't drinking recycled sewage. That doesn't stop everyone, though. This is a famous software entrepreneur with a device that he was interested in. It's another waste treatment plant which produces water right on site. And so this is very much a part of it if you can just get past the ick factor. So I'll stop there. I want to thank the people who do all the work, which are the students in my group. They have all the brains and all I do is direct. So thank you.
We have some time for some questions.
How does the batch down RO process compare energy-wise to recovering the pressure from the concentrated vegetables?
So the pressure recovery is standard in most large seawater plants now. And those plants come in with energy of around 2.5 kilowatt hours per cubic meter in that frame. The batch process is under 2, depends a bit how it's designed. But you're saving on the order of 30%, depending on salinity and water recovery ratios. But 30% is a good estimate. So that's a lot.
Are there any plants being built with that on a full scale?
Most of the plants that have been built at this point have been built by the company Desalination that I mentioned, based here. They're typically doing something other than seawater. They're typically working with low salinity waters, either brackish groundwater or certain processed waters in the food and beverage industry. And so in their case, they go to high recovery on the water. And the pressure exchangers are effective because you have a significant amount of energy in the discharge brine. And the more water you recover, the less brine you have. And as a result, the pressure exchangers don't become important for those processes. The question is whether you can get this done for seawater. And the batch process is promising that way because it gives you the opportunity to avoid needing a pressure recovery device.
John. Sorry.
I'm sorry, Pete, and then you.
Oh, sorry.
I noticed you had reference to a plant in Tampa, and I think that was if I remember correctly, that was quite a problematic startup, wasn't it? I wonder if you had any insights as to what happened there and what lessons could be learned from that?
Well, the Tampa plant and also the one that was built in Santa Barbara a long time ago, they had a number of issues. I'm less familiar with the detail of the Tampa plant per se. I think some of it had to do with the pretreatment that was involved and issues with fluctuating water quality. One of the biggest variables for membrane desalination is if you have things like algal blooms, if you have too much silt, some of these issues in the feed water. The membranes don't tolerate it very well, and unless you're dynamically able to change the pretreatment, you can have issues. Most of those plants have some type of ultrafiltration on the intake, which gets you so far, but then if you've got toxins or smaller things, ultrafiltration is not enough. The Santa Barbara plant was one of the very early ones built in the U.S. It was about 1991 or 2. It was put up during a drought, and then the next year it rained and filled up the reservoir. They ran the thing for like 3 or 4 months and shut it down because it was no longer economic or needed. It's being retrofit now as a result of the current drought, and perhaps will actually come online and run. But a very general problem, to your point, is that if the feed water has varying quality, particularly algal blooms, the plants can get shut down. And there are a number of instances around the world where harmful aquatic bacteria and other things have caused plants to shut down for a couple of days. There's a plant in Chile, not the one I mentioned, but up the coast a little bit. That was shut down for 3 or 4 days by an algae bloom. The problem is they didn't have much reserve capacity. And so if you don't have an alternate or a reserve source, if you're 100% dependent on that and your plant shuts down, you have a very big problem.
John, the example that you gave from Singapore with the used water, what's the main source of that? Is that municipal wastewater or?
Municipal wastewater, yeah.
Do they use any industrial wastewater?
I want to be careful because I don't know the breakdown. I don't know if one of my colleagues who spent some time in Singapore can answer that.
It's mainly?
It's mainly sewage. I mean, it's whatever went into the waste stream.
I was glad to see your mention of forward osmosis in one of the charts that you showed. As a new technology, I was wondering if you've done a thermodynamic calculation, or you've seen one done that compares the minimum energy required for FO versus RO.
Thank you. Yes, in fact, we published on this topic. Forward osmosis came to the fore perhaps 5-10 years ago, actually around 2006 or 7 in that time frame, with some expectations that it might be lower energy. The way the forward osmosis process works is that you have a membrane with, say, seawater on one side, saline water to one side, and a much saltier so-called draw solution on the other side, so that water will flow from seawater through the membrane into the draw solution with minimal electrical pumping. You don't have to pressurize it much because it's going osmotically. Then you've got some other process in the background that accomplishes the separation of water from the draw solution. One process that's been looked at a lot is the thermolytic process, where you've got carbon dioxide and ammonia solution, which you can heat, then vaporizing the ammonia and carbon dioxide and leaving the water. Other processes involve a draw solution that you could purify using reverse osmosis, but perhaps without concerns about fouling the membrane. Very pure salt of some sort. So the forward osmosis process was originally considered just in terms of the pumping work, and people didn't remember the thermal energy that was used in the thermocatalytic part. And when you put the thermal energy requirement back in with the electrical energy together, you found that it wasn't such a big reduction in total energy use required. In terms of forward osmosis that uses reverse osmosis as the separation step, you can actually do a simple thought model. I start with water in seawater at this Gibbs energy. Pure water has this Gibbs energy. The work of separation is to raise the energy of water in seawater to the pure water value. The forward osmosis process begins by taking it from the seawater Gibbs energy to the draw solution Gibbs energy, which is even lower. And then you've got to provide the energy to get back to the pure water state. And so you've dug a hole that you have to get out of. Energetically, forward osmosis doesn't have strong advantages, but it does have advantages for pretreatment. It's being looked at for a number of waters that are difficult for standard RO, where you can take water out of solution, get into the nice draw state, and then use reverse osmosis to purify it. I've been through some discussions with people in the industry about this, and they will argue that it would not be possible to treat that water at all using reverse osmosis because the pretreatment requirements are too severe. So use the FORO process, and then at least you can get somewhere. So my point on forward osmosis then is that as a direct head-to-head competitor with reverse osmosis for seawater, it doesn't win. But when you look at pretreatment requirements for difficult waters, perhaps something that's got high fouling potential, perhaps something that's very saline, forward osmosis has niche applications that look quite economical. So.
Bob, the question. You brought up the Santa Barbara plant, which was commissioned and decommissioned, and they come back in response to drought conditions. Does it ever make sense to design desal for peaking or cycling basis, or does it really need to be for baseload?
That's a good question. I mean, ideally, you'd like to run the plant more or less full-time if you can, because you've got a lot of capital invested in it. If it's an efficient plant, it's going to run continuously. Your ideal would be to run it continuously. The question of whether it makes sense or not, when you don't have water and you need the water, then you might be able to justify it, as in comparison to alternatives. And that again depends where you are and what your choices may be. In the case of California, the choice, conservation is part of the answer. Can you transfer more water in the aqueducts? No, not really. Can you make it rain more? No, not really. So there is a motivation to try and meet needs that way if you can't do it by recycling and conservation first. But if you go to some other parts of the world, you may not even have those options. And you know, I've had this conversation with people from parts of the Middle East who say, look, without the desalination, we have nothing, no water. We would not be able to provide water for our families or for our cities or for anything else. A country like Kuwait is getting 100% of its water by desal. The Saudis get more than 70%. UAE gets about 97%. And so those societies could not exist as they currently do without having some source of desalinated water. But you know, the trade-off really has to be looked at in context, and every context is a different situation. Singapore is another interesting case. They're getting about a quarter of their water from desalination. They're aiming to get about half of it from recycled water and the balance from catchment water. But the reason they want to do that is because their traditional source, which is a pipeline from Malaysia, is one that they consider to be politically unfeasible. Singapore was formed when it was kicked out of Malaysia by the Malaysians. They have a pipeline that was their original source of water, and periodically when the Malaysians get mad at them, they threaten to cut off the water. As a matter of national security, you don't want to be dependent on a source of water that somebody can close the tap on. So, you know, that's part of the answer. The plants themselves can run intermittently. They run better if you just run them steadily. So, you know, peak loading, you know, on and off during the day by itself may not be the answer. There is something you can do, though, if you have tariff pricing on electricity. You can make water and store it when the price of electricity is low. And then you can use the electricity not for RO, but for your cities when the price is higher. And so there are ways to do load balancing in that way that are a little different than meeting mean demand. So.
In the back?
Yeah, John, in terms of the, I've read some statistic, I don't know loud enough, is that for somewhere around, I think it's 40% or plus of the water consumptions for in America is for, goes towards energy, the other 40% goes towards something in the agricultural processes. And when you look at desalination, the expense, and the sort of CapEx requirements, have they looked, and you guys looked at models, because obviously the water quality criteria, you know, when you're talking about, you know, the sort of treatment process, in terms of helping with those sort of policy decisions, you talk about the cost of water, and have they looked at that integration of that, those sort of issues? Because, you know, you're talking 80%, I think, you know, versus, you know, personal consumption.
Right. So yeah, the breakdown of water use in the U.S. is about 40% for cooling power plants, water withdrawal, I should say. About 40% of the U.S. or a bit more would be for agriculture, for irrigation, and the rest is for commercial, industrial, domestic use. Domestic use is less than 10% of water consumption in the U.S., water withdrawal in the U.S. Worldwide, irrigation is actually more like 70+% of water use. The U.S. is a little unusual in that regard. The water that's used in power plants tends to be once through cooling. That's the biggest user. So you're taking surface waters, you put it in back warm. It's a little bit of a misleading figure to that extent. But there's a lot of interest in the question of whether you can use desal water for irrigation and to do something to offset surface or groundwater requirements that way. Most cases, the cost of water through desalination is much higher than what you would pay, what farmers typically pay for groundwater or for surface water. The water rights are given. In some cases, people are not paying really much at all for that water. And so the economics are a little bit of a challenge when you look at using desal to replace irrigation water. There are some projects in California, for example, Chevron produces a lot of oil and gas. That water is being treated and used for irrigation in some places in the Central Valley. The Spanish have actually used seawater reverse osmosis for irrigation. Everything I've heard suggests that that wasn't a great economic decision. But one place where it's been done very successfully and in an integrated way is in Israel. The Israelis are just leaders on water because they have to be, and so I reference them a lot because they've done so much in this regard. But in Israel, they're getting most of their water from seawater reverse osmosis at this point. They also recycle most of their wastewater, and so they're reclaiming 70% or so of the wastewater. It's being used for irrigation, and so they'll treat it and then they'll send it off to grow crops in the desert. They're very frugal about the water. The water then that is being reclaimed and reused has as its source the reverse osmosis process. And that in that instance, it starts to look economical. Occasionally when they overproduce desalinated water, they'll send it directly to irrigation. But there are some challenges, because when water goes through municipal use, it picks up ions. And so if you've treated the water for municipal use, you've set the chlorides at some level, it comes out as wastewater with a lot more chloride in it. If you take the water in that condition and use it for irrigation, you kill the crops because they're sensitive to what's in the water. So they actually have to desalinate more than would strictly be necessary to lower the chlorides, especially to lower the boron in the water. They'll do a second pass of RO to get that down so that by the time it comes out as treated municipal wastewater, the chlorides are down to a level that the plants can tolerate. And then there are other things that you can think about as you start to desalinate brackish groundwater. For example, plants love magnesium, calcium. And so if you're going to desalinate groundwater, you'd kind of like to leave some of the magnesium and calcium in it while you take out the sodium and the chloride. And so can you do things that are sort of like making designer water through a desalination process? So there's a spectrum of issues there. The short answer is desalination is not usually a very economical way to irrigate crops.
Anyone else? Okay, thank you again.
Thank you.